Okay, it's Brian here. We're going to do some more slides having to do with force and motion. We're going to look at a couple more problems. And these ones are ones which have a little bit of angle stuff going on. We've been looking at ones which are mostly horizontal and vertical. Now it's time to get angular. So let's take a look at this one. And this is a one with biological kind of like importance. We're looking at forces in the knee joint. And so the question says this: if there's 500 newtons of tension in the tendons shown in the diagram, right here, the quadriceps tendon and the patella tendon, what is the magnitude of the force from the condyle of the femur on the patella? And by the way, this was a problem that was suggested by somebody in the class, and somebody in the class also taught me all these words. So thank you to somebody in the class who kind of like brought this to my attention. Now, you look at this problem, you're thinking like, oh my gosh, how do I solve this problem? The way I solve this problem? It's the way we solve every single problem. The way we solve every single problem. First off, we do a motion diagram. Well, in that case, it's easy. The motion body diagram. The patella, we're going to look at the motion. We're going to look at the forces. Second, remember, that's how we solve problems. Now, for the motion diagram, it's pretty easy. Here it is. Here's the patella. The patella is you do not want your kneecap accelerating. It would be bad. So there we go. We're going to draw a free body diagram. If it's not moving, that tells us we have a couple of steps that we can do after that. We're going to look tells us that net force, write down expression for the x and y components of the force. Now that's going to be really important to inform what comes next, because what comes next is we're going to draw a free body diagram, and the sum of the forces has to be equal to 0. Now, if you look at the forces on the patella, there's an upward force from the quadriceps tendon. There's a force that goes in this direction, okay, that's due to the patella tendon. And then there's a force in this, well, let's see, I have to balance this. I need a total force that looks like it's 0. And we said it's a force from the femur on the patella, and I think it kind of needs to push in that direction in order to make everything balance, okay? And what type of force is it? Well, it's basically perpendicular to the surface. The patella is going to rock back and forth until it's sitting, so that the force on it is a normal force. Whenever we have forces at surfaces, there can be a normal force, there can be a friction force, but you don't want friction forces in your joints. You're not at that age yet. I am. You don't want friction forces in your joints. So let's assume it's just a normal force. Okay, so I got a normal force right here. And I have a force in the quadriceps tendon, that's a tension force. And I have a force in the patella tendon, and that's a tension force as well. Now what we're going to do next is we're going to draw like a larger scale version of this free body diagram so that we can write down expressions for the x and the y components of the force. Okay, we're going to do that. So what I'm going to do is I'm just going to erase everything that's here. Okay, so I'm just going to go ahead and erase everything. Okay, still important, but we're just interested in kind of like making a bigger version of this diagram. We know the net force is equal to 0, and that has informed our drawing of the motion diagram. Okay, here we go. So here's my patella. That was a little big. Let's get a smaller pen here. Okay, so here's my patella right here, and the forces acting on it are an upward 5,000 Newton force. Okay, and I have a force going in this direction, and again it's 5,000 newtons, and it's acting at an angle that is 42 degrees with respect to the horizontal. So this is a 42-degree angle. And then I also have a normal force which is heading in this direction. Okay, now what I'm going to do is I'm going to set up x and y axes. So there's my x-axis. My y-axis looks like this. And then I'm just going to break vectors into components. Now the 5,000 Newton force from the quadriceps tendon is acting straight along the y-axis, so that one's good. The 5,000 Newton from the patella tendon is acting at an angle, so I can break it up into components. And I have a component in this direction, and that is adjacent to the 42-degree angle. So the value of that one is going to be 5,000 newtons times the cosine of 42 degrees. And then I'm going to have a vertical component that's down here. That one is going to be 5,000 newtons times the sine of 42 degrees. Then for the normal force, really, I can't say too much about it, but I can say, look, I'm going to break it into a y component, which I'll call ny, and a horizontal component, which I will call nx. Now remember, when we break vectors up into components, the vectors are basically equivalent. The components are basically equivalent to the vectors that were there before. So now what we can say is like, oh, so really, this normal force, I broke it up into components. Normal force, you are dead to me. We can get rid of it. We can get rid of it. We don't need that. There's not the normal force vector. There's just the components. Same thing with this thing at a 42-degree angle. That thing is now dead to me. It's not dead to me. It doesn't exist. There's just the vector components. And so I can look at the forces that act along the x-axis and ones that act along the y-axis. Man, we are getting perilously close to solving this problem because we know that the net force is equal to 0. And if the net force is equal to 0, okay, that's the net force along the x-axis and along the y-axis. So the x components have to sum to 0, and the y components have to sum to 0. And check it out. If the x components are equal to 0, that just says nx is equal to this. And if the y components are equal to 0, the upward force, 5,000 newtons, is just equal to the total downward force, which is ny plus 5,000 newtons times the sine of 42 degrees. And so I can write down two expressions that basically allow me to calculate everything. And that's what we have to do here. Now, the expression for the x component we wrote down was this. We said if the x component force is equal to 0, that nx, which is going to the left, the magnitude has got to be equal to the y, the component going to the right, and that was 5,000 newtons times the cosine of 42. For the y component, we said that the normal force in the y direction, okay, plus the 5,000 newtons times the sine of 42, which was the forces pushing downward, is equal to 5,000 newtons, which was the force pushing upwards. So we just did the sum of the forces on the x-axis and the y-axis and ended up with two expressions. And with those in hand, I can figure out the magnitude of the x and the y components of the normal force. And with that in hand, I can find the magnitude of the force. And if I do that, I get a magnitude of a force of about 4,100 newtons. And let's just do a quick assessment. If I draw a vector force on this diagram that kind of points out like so, it's going to be slightly smaller than this one or than this one. It seems like it has to be about the same size, and that seems reasonable. But you look at this and you're saying like, oh my gosh, Brian, that's a force of about 800 pounds. So you have a force of 800 pounds between your femur and your patella. There's a huge force at this juncture. How would you do this? And I will show an example in class very, very soon whereby performing something very, very ordinary and everyday, I require a force of 5,000 newtons in the tendons that are holding my kneecap in place. And I'm going to get a force that's that large in my knee. And actually, after I demonstrate this in class, my knees hurt a little bit, okay? This is reasonable. It's surprising, but it's actually true. And that's our assessment. Now there's a slide on the homework assignment that you have to do. There's a person on a slack line. And you can treat it this way. I can say, look, let's look at the point in the rope. Okay, the person is pushing down in that point in the rope. Two tension forces are pulling up, and I can sum force vectors to sum to 0. And that's how you can get the tension force. Let's look at one more problem today, and we're going to look at this one. So this is about the Pikes Peak cog railway. And the cog railway has wheels that have like they're little cogs. I guess it's a cog railway, so that's not a huge surprise. And the cogs, they're like tooth gears. And the tooth gears kind of like grab a hold of teeth on the track as the thing goes. And so it can go up the slope without slipping. Why would you need to do that? And the answer is steel on steel is actually pretty slippery. Wet steel on wet steel has a coefficient of friction of only 0.15. That is slippery. That is less than ice. That is less than your shoes on ice. Very, very slippery. So the question asks this: could a normal train car climb the average 9-degree slope of the Pikes Peak Cog Railway in the rain? Okay, and here's my pre-assessment. It's a cog railway. They put cogs in for a reason. And so I'm going to guess that the answer is no. I'm going to guess that. And if my answer comes out to be no, I will say awesome, because that's kind of what I expected. That's our problem. How do we solve it? Oh, you little scamps. We solve this the same way we solve every problem. First off, we have to do is strategize. Question, what are we solving for? What are we solving for? And here's what I'm going to do. I'm going to say, let's take a look at this train car. And let's look at the forces that are making it go up the track. Let's suppose we assumed that basically there wasn't a cog. It was just friction of steel on steel. Let's calculate what the friction force would have to be. Then we can ask ourselves, is it possible that the friction force could be that big? Can it be that big? And if the answer is yes, it could climb it. If the answer is no, it can't. So let's just solve what friction force would be necessary and then ask ourselves, is it possible? That's my strategy. And the way we continue, of course, is the way we do every single problem. We're going to draw 1, a motion diagram, 2, a free body diagram. The motion diagram is just the car is climbing up the hill. And let's assume that it's climbing up the hill at a constant speed. Let's assume the person is like goosing the accelerator and trying to pick up speed. The acceleration is equal to 0. And so what that tells us about the net force is also equal to 0. And we can use that to inform our free body diagram. And the free body diagram looks like this. Okay? I'm going to have a normal force, which is perpendicular to the track. I'm going to have a friction force, which is parallel to the track. And I have a weight force, which acts straight downward. Okay? Now, I'm going to do an unusual thing in this problem. What I'm going to do is take a non-traditional x and y axis. I'm going to take a y-axis that is perpendicular to the slope. So my y-axis is going to go like this. Okay, that's my y-axis. I'm going to take an x-axis that is parallel to the slope. And so it looks like this. Okay? I'm going to take those axes. Now with that in hand, you can see the normal force is along the y-axis, the friction force is along the x-axis. Okay, so that's going to simplify my problem solving. The weight force is at an angle. We know what angle it's at. It's at a 9-degree angle. Okay, it's at a 9-degree angle, and we can use that going forward. Okay, next piece of the puzzle, set up a coordinate system. Oops, got ahead of myself. I already did that. So I can go ahead and redraw that coordinate system, and then I can find the components of W. So let's go ahead and redraw. And if we do that, we've got the normal force, which is pointing like so. I've got a weight force, which is pointing straight down. I have the friction force, which is going up the track like so. That's my Fs, that's my W, that's my weight. Oh, and quick aside, we assumed it's static friction because we do not want the car to slide. Okay, so my y-axis goes like so. My x-axis goes like so. And then I'm going to break the weight force into two components. I've got a component that is along the x-axis right here. It's going to be going that way, and one that's along the y-axis. Okay, so I've got my wx and my wy. Now I'm going to note this angle right here. This is a 9-degree angle, and I want you to think about why that would be true. But the slope is tipped at a 9-degree angle. The weight force is at a 9-degree angle with respect to the slope. So I can use that to write down expressions for W. Wx is just going to be equal to the hypotenuse W times the times the sine of 9 degrees. Because if we took that W vector and we made it be down here, it is going to be on the opposite side of the triangle. Wy, on the other hand, is going to be equal to W times the cosine of 9 degrees. Okay, we got that. Now remember, when I take a vector and I break it into components, basically that vector, it's dead to me. It's dead to me. We took it, we broke it into components. Basically, we replace it with the components. And so we can get rid of that weight force vector. It is no longer a thing. So cover that up. And those are the 4 vectors that remain. I've got Wx, I've got N, I've got Fs, and I got Wy. And that is it. That is it. Now, we can write down an expression for the x components of the force and write down an expression for the y components of the force. I'm going to do that by reminding you what all the different things are. So I have a y-axis that goes like so. I have an x-axis that goes like so. And remember what our forces were. We had a normal force that was this way. We had a force this way, which was my static friction force. I had a force that was this way. That was W times the sine of 9 degrees. And had a force that was along this axis. That was the vertical component of the weight. That was W times the cosine of 9 degrees. So those are my expressions for the forces. And then we can write down an expression for the x components of the force. Well, remember, we know this is true. F net is equal to 0. We said that because it's climbing at a constant speed. There's no acceleration, no net force. So my expression for the components of the force are just this. Fs has got to be equal to W times the sine of 9 degrees. N has got to be equal to W times the cosine of 9 degrees. That's got to be true. So those are our expressions for the x and y components of the force. Since F net is equal to 0, the force that points perpendicular upward is equal to the force that points perpendicular downward. The force that points up the slope is equal to the force that points down the slope. Everything's got to balance that way. Now, if this net force is equal to be 0, we can determine the minimum value of the coefficient of static friction, and we do it this way. Let's rewrite our expressions, and we said Fs was equal to W times the sine of 9 degrees. We said the normal force was equal to W times the cosine of 9 degrees. Now we know the static friction force is less than or equal to mu s times the weight, right? We know that mu s times the normal force. We know that that's true. So that tells me Fs over N better be less than mu s. The necessary static friction force divided by the normal force better be less than mu s. And we know what mu s is. It's equal to 0.15. Okay? So we're assuming that the thing can work its way up the track. And I want to look at a ratio of Fs over N. Well, the ratio of Fs over N is equal to, and I'm taking these expressions right here, and I bring them over. Fs over N is equal to W times the sine of 9 degrees divided by W times the cosine of 9 degrees. Oh, check it out. This is very, very handy. W is going to cancel between the top and the bottom of the expression. And I know what sine over cosine is. That's just equal to the tangent of 9 degrees. And I can work out the tangent of 9 degrees, and that's 0.16. So we went ahead and we solved for the necessary friction force to make the car go up the ramp. And the ratio of the friction force to the normal force is 0.16. But what we know about friction force tells us that this ratio has to be less than 0.15. So the net result is no worky. Okay, you can't do this. You can't do this. The car is not going to work its way up the track in the rain. And so it would be awesome. You start out on a sunny day. Everybody's going along just fine. You're working your way up the Cog Railway. It starts to rain, and the thing slides on the slope, picking up speed until it slams into the station at Manitou Springs. That's not the kind of trip that people signed up for. Now, and so our assessment is To be able to make this thing make it up the slope, you would require a minimum coefficient of friction of 0.16. The actual coefficient of friction is 0.15. And so how do you solve this? You need cogs. And so we're expecting it not to be able to make it up the slope in the rain, and in fact it can't, so it matches our initial expectation. Now I want to point something out to you. When I started this problem, I didn't know where I was going. I did not know. This is true. Like, sure, I wrote this problem, but I wrote this a while ago, and I forgot what the solution is. I don't remember the details of this problem. I didn't even have a fully formed, I didn't even have a fully formed out path to the solution. But what I did know was I had a strategy. I had a plan. I said to myself, you know what? If I just dive into this problem and I go ahead and I write a motion diagram and I write a free body diagram, and I just start taking components and doing the same things I always do, I will end up in a happy place. And so I didn't know how to solve the problem, but I knew how to start the problem. And that's the key thing. And a lot of folks say you don't know how to get started. Well, in these problems, it's easy. How do you start? Draw a motion diagram, draw a free body diagram, take components, write expressions for the net force on the different axes. And if you want to see examples of how this process works, we've got a zillion of them in the textbook. Well, it's probably an exaggeration. We have several in the textbook, and then you can also look at the video tutor solutions, et cetera, and Heavens Betsy, you can look at the examples in these very slides. Now, the next piece that we're going to do is we're going to talk about circular motion. So it's another force and motion thing, but we're going to look at things which are going in circles, as Carol and I are on the Carousel of Happiness, which if you haven't been to the Carousel of Happiness, it's in Netherlands and you really have to go. Next time, circular motion.